Okay, so let's start. So thank you everyone for participating in EPSP Connect's monthly virtual seminar this March. Before starting, I just want to remind everyone that the purpose of this series is to bring the community together and to help establish connections between people who might not be able to interact with others in a different setting. So we all are very happy to have you here. I want to also thank all the EPSP Connect team members who help plan and organize the series, who reach out to potential speakers and coordinate with them, and who advertise in social media and make sure that the series information is up to date on the website. So joining me today as a co-host is Shashank Anand, who will help us with a Q&A session at the end. Shashank, can you share with us what is the plan for today?
Thank Michelle, and hi everyone. This is Shashank. Please post your questions in the chat and Michelle and I will monitor them. If you prefer, we are also able to ask you to unmute yourself and ask the questions directly. For those who are listening us on our live stream on YouTube, we'll also keep an eye on those questions that are coming there.
Thank you very much, Shashank. So now our speaker today is Dr. Anastasia Piliouras. She's an assistant professor in the Department of Geoscience at Penn State University, and she received her bachelor's in earth science from the University of Pennsylvania and her PhD in geological science from the University of Texas at Austin in 2016. Previously, she worked as a staff scientist at Los Alamos National Lab, where she also did her postdoctoral research and became interested in high latitude process. Dr. Piliouras, please take it away.
Great. Well, thanks for the introduction and for inviting me. And I'm going to slowly share my screen. I swear I practiced it. Let's see. All right. I assume you see this. I'm going to start talking. So, okay. Today, I am going to share with you some research that we've been doing on high latitude deltas and really thinking about these landscapes as conduits for land-ocean fluxes. So this is work that I've been doing over the last 8 years or so in collaboration with Joel Rowland, who was at Los Alamos National Lab, as well as Selma Organ, who is an undergraduate at Penn State. Okay, so we're in the Arctic. The Arctic Ocean is quite small. Here you're seeing the Arctic Ocean at the middle, looking down on the North Pole, a bunch of large watersheds draining into this relatively small ocean basin. The Arctic Ocean holds only about 1% of the world's seawater, but it receives a disproportionately large amount of river flow. So it holds 1% of the world's seawater, and it receives more than 10% of the world's river discharge. So we've got a bunch of these really large watersheds that drain the northern slopes of continents, and they pump a whole bunch of water, also sediments and nutrients and heat into this relatively small ocean basin. And so over time, Arctic rivers have helped to influence the temperature and salinity of the Arctic Ocean through contributing those fluxes. But we know that rivers are not pipes, right? They interact with the landscapes around them, and at the mouths of rivers sit river deltas. And deltas are really important landscapes because they could alter the timing, the location, or even the magnitude of some of these land-ocean fluxes that can really affect climate as well as marine ecosystems. So this image on the left is a schematic from a paper by Matt Hyatt and Paula Passalacqua, and it shows you some examples of these possible transport pathways through river deltas. So we've got the potential to just transport water through the main distributary network. That would be quite straightforward and also quite quick. But you also can transport water and waterborne constituents through some of these smaller secondary channels. Some of those might be bidirectional. You could have transient storage in wetlands or lakes, or permanent storage if you're depositing sediment. You might have overbank flow. You might deposit sediment on the delta plain. So the transport pathways through these deltas are really a lot more complex than just the distributary networks. And understanding those transport pathways is really important to understanding how these deltas function, and also requires us then to understand the morphologies and dynamics of deltas themselves. So when we think about delta morphology and dynamics, I think a lot of people think about this ternary diagram that you've probably seen before. that gives you these kind of primary controls on delta morphology of rivers, waves, and tides. And of course, there's a continuum here. There's a spectrum, right? So deltas can be influenced by multiple different things between rivers, waves, and tides. And more recently, people have shown that a lot of other stuff like grain size, basin depth, vegetation, cohesive sediment, all of this can influence the morphology of the delta and the dynamics of the delta as well. I would say climate also is going to have a large impact on delta morphology and dynamics. So it could affect, of course, these three drivers. So your climate might influence, in particular, the waves that you're experiencing at the coast, but it also affects the local conditions where the deltas are. And at high latitudes, it can be really important because we have these unique conditions of permafrost and ice cover that might affect delta morphology and dynamics. So permafrost, for those not familiar, is just land that remains frozen or remains below 0 degrees C for at least 2 years, never thaws. This map on the left here is of Alaska, and it shows you the likely absence or presence of near surface permafrost. So permafrost in the upper meter of soil. And I've drawn on here the locations of the Yukon Delta and the Colville Delta, which are two of the systems we're going to look at today. So the Colville Delta is up here in the North Slope of Alaska. This delta is likely entirely underlain by near surface permafrost. The Yukon Delta is a bit different, really kind of patchy permafrost remaining at this point quite a bit farther south in Alaska. But even with the difference in spatial distribution of permafrost, we don't really understand how the presence of permafrost in general might influence flow and transport through these systems or large-scale system dynamics. Then on the right side of the slide, you're seeing a Landsat scene of part of the Lena Delta in Russia, another delta that we'll look at today. And the scene was captured on the day of peak discharge in June of 2015. And all of this bright blue, this kind of cyan color that you're seeing, this is ice and snow. So on the day of peak flow in the Lena River, you have over 150,000 cubic meters a second of water coming down the river. And a lot of this delta is still ice covered. What does ice then do to flow and transport through the system and to the dynamics of the delta? So today we're going to talk about Arctic deltas and try to understand their morphologies and the variability in their morphologies between some of the largest Arctic deltas that we have. We'll also try to understand something about delta dynamics, these unique Arctic influences, and the coastal transport pathways through the landscapes. And then finally, think about how deltas might influence riverine fluxes to the coast. So how the deltaic landscapes influence the transport of stuff, but more specifically, water, sediment, nutrients, and heat. How do deltas influence the transport of those fluxes in terms of the timing, the spatial distributions, or perhaps the magnitudes? So we're going to focus on these 6 deltas that you see here. So we've got the Colville Delta up on the North Slope of Alaska and the Yukon in southwestern Alaska. You saw those two already. Then we've got the Lena, the Kolyma, and the Yenisei. These are all Russian deltas. And then the Mackenzie Delta in the Northwest Territories in Canada. And we're using Landsat imagery to look at these deltas and to classify the land, the channels, and the lakes. And that's what you're seeing in this image. So the land has been classified as green, the lakes as blue, and the channels as this light blue. You'll notice there's some yellow in here as well. I'm not going to go into detail about that today, but that is small water bodies that we tend to exclude from our analysis. So we did this classification using an object-based classification program called eCognition, generate these masks, and then use those to quantify metrics that tell us something about delta form and function, looking at the islands, the channels, and the lakes. And we'll kind of step through just a couple of those metrics today. So I'm going to start really large scale looking at the whole delta and specifically looking at the delta islands. So delta islands can be really informative because they tell us something about channel activity and perhaps also something about delta resilience. So channels make new islands. Those new islands tend to be small. Where you've got lots of small islands, you might think you have more channel activity. So this map is showing you normalized island sizes on each delta. So the size of an individual island normalized by the total area of the delta. So where you've got lots of red, you have lots of really small islands. And where you've got greens and blues and purples, you have larger islands. And hopefully something jumps out at you right away, which is that we've got these three deltas, the Colville, the Colima, and the Yukon, that have kind of a mix of island sizes, some big and some small. And then you've got three, the Lena, the Mackenzie, and the Yenisei, that have all small islands. So already from this one metric, I would say there's some morphologic variability between these six deltas. Now, why this is important is because we can look at the island size and the related metric of channel density to understand something about not only channel activity, but also delta resilience. And by that, I mean thinking about how these channels distribute fluxes across the delta plane. So if you took a slice through the delta, closer to a channel, here you're seeing a channel cross section. If you're closer to a channel, you have more frequent delivery of sediment and nutrients. The farther you get from a channel, right, the harder it is to nourish or grade these areas. So in systems where we've got really large islands, we've got these really long transport distances where it can be difficult to deliver sediment and nutrients to the top of the delta. Compare that to something with a higher channel density with these smaller islands. This system on the bottom would be relatively easier to grade. So in the context of our six deltas, I would say that the Colville, the Colima, and the Yukon with all these really big islands would be relatively harder to nourish and harder to grade in the face of possible relative sea level rise compared to something like the Mackenzie, the Yenisei, or the Lena, where we've got this high channel density, lots of small islands. Those are going to be a little bit easier to nourish and grow. Okay, so returning to our research questions, already we've identified some differences in the island size distributions across these six major deltas. The differences in island sizes that we observe also suggest some differences in resilience in the face of potential sea level rise and also in the ability to nourish and grade the delta plane. Whether this tells us anything about formative processes yet, we don't really know. But the islands, in addition to the channels, are really the building blocks of these systems. So we're going to now poke at the channels and see if we can understand something about the channel networks in these systems, what affects their formation and structure, and also start thinking about the channel networks as the main coastal transport pathways for these systems. So to talk about the channels, today I'm going to focus just on this one metric. Of course, there are many more we could look at. And this metric is called the evenness number. This is a metric that we designed specifically to understand how fluxes are distributed along the coast. So it gives us a sense of how evenly or how uniformly channels are sized and spaced near the shoreline, channels there being the proxy for fluxes. So the evenness number, very simply, is just the mean channel spacing times the mean channel width divided by their standard deviations. Written another way, it's 1 over the coefficient of variation of channel spacing. And we measure all of these variables along this red transect. And this red transect is a line that's parallel to the shoreline of the delta, but it's set back about 20% of the delta line. And the reason that we don't define things right along the shoreline is delta shorelines are subjective and they're also kind of noisy. So if we measured something like channel width right along the shoreline here, it's really difficult to say what is actually the channel width where we've got lots of marine influence and where we've got new islands forming. So we just set this transect back 20% and we define our channel characteristics there. Okay, so here we've got the components of the evenness number. We've got the coefficient of variation in channel spacing on the left. We've got the coefficient of variation in channel width in the middle, and then the evenness number on the right for all six deltas. And this is plotted against delta size. In this case, the width of the delta along the coastline. You can think of that as the length of coastline over which deltas could be distributing their fluxes to the ocean. What we see is that the variability in channel spacing on this left plot seems to scale with delta size. So our largest deltas are the Lena and the Mackenzie, and they have the highest variability in channel spacing. If we look at the middle plot, here we can see that the variability in channel width is quite high for all of the deltas, excluding the Colville, where it's notably lower. And if we put that together, then we see that the evenness number is inversely proportional to the size of the delta. And the actual value of the evenness number isn't what matters. It's the relative values between these six systems. So here we've got the Lena delta out here at this blue X. the Lena Delta has over 220 kilometers of coastline where it could be pumping sediment into the ocean, but it does not distribute those fluxes very evenly, compared to something like the Colville Delta up here that does distribute its fluxes evenly or uniformly, but its coastline is quite short, only 20 kilometers. So at a large scale, I would interpret that to say that these 6 deltas contribute their fluxes to the ocean at discrete locations along the coast. We can look at that a little bit more quantitatively. Here I'm showing you those end members of the Colville and the Lena. So you've got the channels are in white, the land is in black. We've got the channel skeleton, the center lines here with these different colors, which are colored according to the proportion of flux moving through each channel. But the really important part to look at here is these pink circles. So the pink circles are sized based on the fraction of discharge that exits each individual channel mouth along the shoreline. If you look along the Colville Delta, we see that the circles are more or less the same size. You've got a couple small ones, sure, but I would say that these fluxes are pretty well spread out along the shoreline. Compared in particular to something like the Lena Delta, where we've clearly got a couple of areas preferentially receiving flow, right? A couple of areas preferentially transporting most of this stuff from the river to the coast. So the Lena Delta has this non-uniform channel distribution and a really large spatial extent, distributing fluxes to discrete locations, compared to something like the Colville Delta, where it is contributing its fluxes more uniformly, but it's a really small spatial extent over which it's actually contributing material to the coastal ocean. Now, what controls the flux distribution and the channel network distribution? One thing that we have found to be really important is antecedent topography. So we've got 2 deltas, the Mackenzie and the Yenisei, growing in confinement. This is the Yenisei up here on the upper right, growing into an estuary, the Mackenzie growing into an old glacial valley. That confinement places a very firm upper limit on the width of the delta, but likely also has some influence on how the channel network develops as well. Then we've got a couple of deltas with terraces within them. So this image here on the left is the Lena Delta, and you can see this kind of orangey brown splotchy area in the upper left. This is called Arga Island, and it is not actually a part of the delta. This is an old fluvial deposit that remains. It predates the modern delta, and the delta has been growing around it. And there's a number of these terraces within the Lena and the Mackenzie as well. So the deltas grow around these large terraces that drives a really high variability in channel space. And it just so happens that our 2 largest deltas have these terraces within them. So that relationship between variability and delta size, not necessarily causal. Perhaps we're just finding that the largest deltas happen to have terraces and therefore have this really high variability in channel space. Now, we also had a really high variability in channel width. And we think that this is actually driven by ice cover. So on the bottom of this slide, you're seeing 2 images of the Kolyma Delta in Russia. The one on the left is from mid-May in 2013. Again, all this bright blue stuff is ice. At this point in mid-May, the hydrograph on the Kolyma River is really just starting to rise as the spring snowmelt flood is beginning. And you can see that there's a little bit of melting in these 2 main channels here where you see the dark blue popping out. So water's flowing underneath the ice, helping to melt the ice above it. 1 week later, May 21, you can see that this 3rd channel has appeared. A channel that was not melted a week earlier, but now has melted out, is conveying flow. And there's a lot more melting in these larger main channels as well. So what this tells us is that the ice seems to melt earlier in the larger channels, while the smaller channels stay blocked by ice. And this is because the smaller channels can actually freeze all the way to the bed if they're shallow enough. So the smaller channels are blocked by ice, the larger channels convey flow earlier, meaning that those larger channels are geomorphically and hydrologically active for a longer period of time than the smaller channels. And so over long time scales, this could actually cause the larger channels to grow larger to accommodate more of that flow. and also keep the small channels small because they're blocked by ice for a longer portion of the year and only convey flow for a shorter fraction of time. And so over time, we think that this might actually drive this high variability in width that we see in these ice-covered deltas. So if this is right, then it means that ice helps to preserve those small channels that we see in the deltas, thereby preserving the small islands. So perhaps ice is actually creating a lot of these small islands by helping to preserve the small channels. This also suggests that now there's a temporal variability in that spatial distribution of fluxes that we hadn't considered before, and perhaps also a non-uniform spatial distribution of sediment flux. So maybe there are parts of the delta active for longer that are receiving more sediment over a longer period of time, making them more resilient in the face of possible relative sea level rise than areas that are less active and receiving less sediment. So overall, this means that ice cover could control channel density and island sizes, as well as sediment delivery to the coast, overall having a pretty strong influence on delta resilience. And so thinking about these systems in the future as the Arctic continues to warm, as we lose ice in these areas, this likely means that we would lose a lot of those small channels, decrease the channel density, and therefore make it more difficult to distribute sediment across the delta plain to help these systems upgrade. So overall, I would say ice has a pretty large role in delta dynamics in channel network structure, at least from what we have seen in our observations and also from some modeling work that I'm not showing you today. We haven't yet talked about permafrost, so I'm going to hard pivot to talk about lakes on Arctic deltas, which are a really unique permafrost feature. So these images that you're seeing on this slide are all from the Colville Delta. The Colville Delta and Arctic deltas in general have a variety of different lakes within them. We've got your kind of classic oxbow lakes. We've also got some abandoned channels on the delta plain that functionally behave like lakes. Those make up about 10 to 15% of the lakes that we see. Most of the lakes are thermokarst lakes. These are a unique permafrost feature. Thermokarst lakes form when you've got water that pools over the frozen soil. That water holds heat. The heat is transported into the soil, which thaws the permafrost, melts the ice, and as you lose that volume, the land subsides, growing the depression, meaning you can hold more water and hold more heat and continue to grow the lake over time. So these thermokarst lakes really cover Arctic deltas. So these are maps showing you the locations of all of the lakes, as well as the percentage of the delta islands that are covered by lakes. We can think of these lakes as potential reservoirs for sediments, and in general, just potential storage sites for water, whether it's permanent or transient for different constituents. And so overall, if we can say that the higher lake cover you have, the greater potential for storage you have, then it looks like the Colville Delta here, 25% lake cover, and the Mackenzie Delta here with 28% lake cover, have the highest potential for storage of sediments and other waterborne constituents. Compare that to something like the Yenisei here on the right with only 8% lake cover, right? So the Yenisei lakes are likely playing a less important role in storage compared to something like the Mackenzie and the Colville, where a quarter of the delta surface is really covered by lakes. Now, all of these lakes are probably not interacting with the channel water in the same way. So if we want to understand the lakes that have the greatest potential for storage, then we can look really just at the lakes that are connected to the channel. So we're going to focus just on the lakes that are structurally connected, meaning there's a morphologic link between a channel and the lake, or perhaps connected by a small tide channel or secondary channel, or lakes that are even chained together. So these structurally connected lakes have the most consistent availability for storage or perhaps biogeochemical changes. And we're using late summer low water imagery. So the lakes we're identifying as structurally connected are likely connected for a wide range of stages because they're connected still in our imagery at low water stage. So if we look just at the connected lakes, we've got two end members again that pop out, which are the Colville and the Yenisei. So in these images, I've removed all of the lakes that are not structurally connected, and I've left just the connected lakes now in green. So the Colville here is on the left, the Yenisei is on the right, and hopefully what you can see is that the Colville has this really complex channel lake network, right? A complex network where water and its constituents has to move not just through the channels, but also through the lakes, in and out of the lakes and channels on its way to the coastal ocean. So understanding the transport pathways through the Colville, significantly more complicated than perhaps something like the Yenisei, where there's really not a lot of green in this image, right? And the Yenisei, we don't have a lot of lakes and we don't have a lot of connected lakes. So if you wanted to understand fluxes through the Yenisei, lakes are going to play a much less important role, and you could likely just approximate things in the channel network and do a pretty good job. On the Colville, on the other hand, not so much, right? We've got to understand how things are moving in and out of this lake channel network instead. Okay, so where are we so far? We've got some differences in island size distributions. I showed you there's definitely differences in lake cover across these systems and certainly in connectivity. There are some possible similarities in the channel networks near shore, and that all of these systems seem to distribute their fluxes to discrete locations along the coast. We've looked at the island sizes and learned something about the resilience and potential for nourishment and aggregation, and in particular, thinking about the role of ice cover in possibly controlling that island size distribution through its control on channel dynamics. So we've got this possible influence of ice cover on system dynamics that has a signature then on the morphology and the island size distribution. And finally, we saw that the spatial distribution of fluxes was controlled by the channel networks. That's perhaps not surprising. I would argue that the lakes are likely also going to play a role in that. And so moving forward, as we think about modeling fluxes through these systems, the lakes really have to be included, particularly in those systems where there's a lot of lake channel connectivity. And those lakes are really a unique permafrost feature. So these are thermokarst lakes, really covering the surfaces of a lot of these deltas that give then a high potential for sediment storage for nutrient processing, and perhaps even delaying the timing of fluxes to the coast. However, so far we've looked really just at a snapshot in time of these systems, right? We're focusing just on what these systems looked like in one image. But deltas are dynamic landscapes. So they're dynamic on short timescales when they flood. This is an example of the Yukon Delta flooding in late May 2006, really inundating a lot of the Delta Plain. So if we're thinking about connectivity, that's going to play a large role. They're also dynamic over longer timescales. So this movie that you're seeing is from some numerical experiments that Rebecca Lozon and I did using Delta RCM to examine the roles of ice and permafrost in longer timescale Delta development. And I'm not going to show you any modeling results today, but I show it just to emphasize that these deltas evolve over time and they evolve under the influence of ice and permafrost. And overall, that the landscapes are changing as they go, right? So for the remainder of the talk, I want to think about how deltas are dynamic, and in particular, how their dynamics might help them to modify or influence riverine fluxes to the coast, specifically focusing on the flux of carbon. So northern rivers export a lot of carbon to the Arctic Ocean. Again, we've got a map, we've got large watersheds draining into this relatively small ocean basin. In these watersheds is a heck of a lot of carbon. So we've got soil organic carbon storage in this map on the upper right. This is soil organic carbon, or SOC, in the upper 3 meters of soil. And this is a pretty recent data set that's quite nice, that gives you a sense of the spatial variability in carbon contents across the northern permafrost soils. So we've got a lot of carbon in northern permafrost soils. We've got rivers draining these watersheds, pumping, among other things, this carbon out into the Arctic Ocean. And the Arctic Great Rivers Observatory, for those who are not familiar, is where this map is from. The Arctic Great Rivers Observatory does a really great job sampling a lot of these large rivers for various waterborne constituents and water quality at these red locations that you see in each watershed. So they sample information about the water, including the carbon content and what's coming out of the watersheds. And that's the data that you're seeing in this table here. So they've got information about particulate organic carbon from each river, dissolved organic carbon, and if we sum those together, we could call that total organic carbon. However, the sampling that they do, and that a lot of people think about for what's coming out of watersheds, the sampling occurs upstream of the deltas. So they're sampling in the river to determine what comes out of the watersheds. But what is actually making it to the ocean? If we sample upstream of the deltas, is that representative of what's actually making it out to the ocean if we've got this whole landscape in between? particularly if we think about how deltas often are net depositional, then it could be problematic, but deltas also erode, right? So here we've got a river bend on the Yukon Delta with an image from 1985. The location of this bend is marked in yellow. And then in 2022, you can see that there's been a lot of erosion around this bend, anywhere from 200 to 400 meters of bank erosion just around this one bend. So as these channels are migrating and eroding, migrating into these carbon-rich permafrost deposits, what influence is that going to have on coastal carbon fluxes? So our goal is to quantify the rates of erosion in these systems and the resulting SOC, or soil organic carbon fluxes. So we're going to return to look at these 6 deltas. We're again using Landsat imagery. We're using the oldest available cloud-free Landsat image, and then an image from somewhere around 2014. And we difference those to determine rates of erosion using a program called SCREEN, which was written by my colleague, Joel Roland. Oh, sorry. Then based on those erosion rates, we're able to estimate SOC fluxes using that carbon map that I showed you for Pan-Arctic SOC data and some estimate of the channel depths that we pull from literature. All right, so erosion rates first. On the upper left, I'm showing you the distributions of erosion rates, so CDF's cumulative distribution functions for the 6 different deltas, and I've divided this into 2 domains, an inland domain and a nearshore domain, nearshore being within 5 channel widths of the shoreline. What we can see is that for most of these systems, the erosion rates throughout the main part of the delta are kind of 1 to 5 meters a year. Nearshore, we can get much higher rates of erosion in some of these systems in particular. There are some deltas, like the Colville, for example, where we've got a lot more erosion shown here in red near the coastline, so some sort of shoreline retreat occurring. In other systems, though, we get a lot of preferential erosion around river bends, like you're seeing here, that same bend on the Yukon. Overall, though, the average erosion rates are fairly similar, around 1 meter a year, maybe down to half a meter a year in some systems. The eroded areas per year are quite different. The Lena Delta in particular, eroding about 10 square kilometers per year. This is the largest delta, so perhaps not surprising that it has the largest eroded area. All right, so that's erosion. How about carbon? Carbon contents are pretty similar across all 6 deltas. The Mackenzie looks to be a bit lower. We're not entirely sure why that is, but overall, the average SOC is about 60 kilograms per square meter for the upper 3 meters of soil. So some of the deltas, or all of the deltas really look quite similar. They look something like the Colima that you see here, excepting the Mackenzie where the carbon content's a little bit lower. So since most of these deltas have similar carbon contents, we would think then that the SOC fluxes should pretty much just be a function of how much erosion occurs. And that's pretty much what we see. So the SOC flux that we're estimating, the vertical axis here, seems to scale with eroded area, which is on the horizontal axis. The Lena Delta up here, again, the largest delta. Alone, the Lena Delta might erode about 2 million tons of SOC per year, and the total SOC export from these 6 deltas exceeds about 2.5 million tons. Now, if you're like me and you're new to carbon, or you're not quite sure how to contextualize that, you could compare that to the estimates from Arctic Grow. So I'm comparing it just to the POC fluxes here, POC perhaps being most comparable to SOC. If I sum up all of the POC fluxes that Arctic Grow measures upstream of the deltas, we have 2.6 million tons of carbon per year coming out of the watersheds. And I just told you that these deltas are eroding about 2.5 million tons a year. So those numbers are pretty much the same, right? So perhaps measuring upstream of the deltas is missing half of what's actually being transported out to the ocean. Now, this is the upper limit of the estimate, right? We're just looking at erosion in the deltas for right now. So this is definitely the upper limit of the estimate of how much carbon could be being eroded out of these deltaic landscapes. We're not considering deposition within the delta. We can map areas of accretion or deposition within the delta with remote sensing, but with remote sensing alone, we're not really able to determine the carbon content of those new deposits. So we can give you at least this upper limit, which is that the deltas might be exporting 2.5 million tons per year of carbon to the ocean, which is on par with what the rivers themselves are exporting. We can look at this a slightly different way. So here I've taken the river POC from Arctic Grow in blue, add it to our estimates of Delta SOC export in orange, and say that the sum of those is the total particulate organic carbon flux out of these systems. And you can get a sense of the balance of river supplied POC versus Delta supplied SOC. And what you see is that the Lena and the Yenisei have particularly large proportions of the carbon coming from erosion within the deltas themselves. This table on the right shows you the same information. It's just got the numbers if you like the numbers, but basically showing you that the ratio of the delta carbon to river carbon is greater than 1 on the Lena and the Yenisei, greater than 2 even on the Lena. So this is a system where you could be having a lot of carbon being eroded in the delta, even relative to what's coming out of the watershed. So overall, I would take this to mean that considering the eroded carbon in deltas could actually increase the POC flux estimates to the coast in a way that's really not captured by current monitoring or observations. Now you might ask yourself, well, could the particulate organic carbon fluxes actually be lower than what they're measuring in the rivers? And possibly, yeah. But that's going to depend on the delta dynamics, right? It depends on the coastal transport pathways, on how things are moving through the system, what's being stored in lakes and bars, and for how long. There's the potential to also just be burying a lot of this in the near shore. One of the things I didn't talk about today is that Arctic deltas have this feature at their shorelines called the 2-meter ramp, which is basically this shallow subaqueous shelf that extends beyond the shoreline at a depth of about 2 meters. And so you could potentially just be depositing a lot of material on this shallow shelf and burying it, which would make it quite a bit less available. So we don't yet know, but the point is that you could be eroding a lot of carbon from the deltas themselves. And we don't know yet how much accretion might be balancing that erosion and what influence that's going to have on the SOC fluxes. So this image on the right shows erosion in blue and accretion in green. This is around a bend on the Mackenzie Delta. So there's certainly a lot of accretion that's occurring in some of these systems, but what it's actually doing to offset erosion specifically of the carbon, we don't yet know. So wrapping up, we have seen that there is certainly quite a bit of variability between these 6 systems based on their island size distributions, based on their lake coverage and lake connectivity. But there's a pretty similar spatial non-uniformity of fluxes that we've identified in the channel networks. I would say looking at the morphologies of deltas in general has also given us some insights about channel activity, about the possible resilience of these systems in the face of potential relative sea level rise, also on storage potential and transport pathways. And we've identified a pretty large role of ice cover in channel network formation, or channel network form and function. And that ice cover then might also help to preserve a lot of those small channels, thereby influencing the island size distribution as well. The effects of permafrost, I would say, on the channel network are less obvious, but there are, of course, these unique permafrost features of lakes that really cover these systems. So thinking about the role of permafrost in Arctic deltas, one of the things we're interested in doing in the future is comparing the natural system dynamics between Arctic and temperate systems to see if there's a difference in, for example, rates of erosion in permafrost and non-permafrost systems. And finally, we showed that channel migration could actually contribute carbon to the coast. So existing measurements that is only considering measurements upstream of the deltas might miss this additional carbon source. And without proper measurements actually at the shoreline, I would say the actual fluxes are really unknown. So if that was all too long for you, the short version is that Arctic deltas are really important landscapes that modify river fluxes to the coast and to marine ecosystems. And ice and permafrost affect delta morphology and delta dynamics, meaning that the future resilience dynamics and function of these systems is really uncertain as the Arctic continues to rapidly. So with that, I would like to thank the HiLab RASM team and DOE funding colleagues and collaborators, and I am happy to take any questions now or over email. Thanks.
Thank you for an excellent talk, Dr. Piliouras. And people who have joined us, you can keep continuing. And if you haven't, please start posting your questions in the chat and we'll start taking them.
There was a question there already, Shashank from Hongboma.
Oh, yeah, just see that. So, the question is, how did you determine the small spatial extent of the Arctic deltas? I'm asking this because I find many satellite images for Arctic delta, and they are distorted due to the projection on coordinate systems. So, do you have any suggestions for the Landsat data processing?
Oh, interesting. Okay. All right, Hangbo. So I have not had this issue perhaps working in some of the larger systems because we're looking at deltas that are, 300, 200 something kilometers wide. I'm not particularly concerned about a little bit of distortion. Maybe I should be. Maybe you should tell me I should be.
Yeah.
But if you're looking
Well,
at some of the smaller systems, then yeah, I would say maybe there's an issue there.
Yeah, well, thank you for the answer. But could you go back to the slides where you show the small spatial extents of the Arctic Delta? So I'm asking this because like we have the resolution of Landsat images as like 30 meters,
Mhm.
right? That's the spatial resolution. Let's say we have like 40 years of the data, right?
Yeah.
Literally, if we want to quantify, either the erosion rate of the shoreline, the highest possible resolution for that is like 0.75 meter per year, right? That's basically the highest resolution we can get. So, we are trying to really like push a limit, but I'm just, quite, kind of surprised to see the result you have, like the erosion rate and the small extent. Yeah. Mm-hmm.
Yeah, I mean so we certainly see if I go to the erosion rates, right? I mean, yeah, we're estimating erosion rates of 1 meter a year. And if we're estimating it over about a 30 years at a 30-meter resolution, then I agree that we're kind of at the limit.
Right, it's kind of a upper limit for the resolution.
Yeah. So one of the other things that we have on our to-do list, and maybe you're doing this too, and I shouldn't duplicate efforts, is to also try to use some higher resolution imagery, but we don't have the long time resolution of that unless we're able to pull kind of older aerial photos and compare with like a more modern planet. So that's another round.
Yeah, there is a slide where you show like the percentage of the small spatial extent. Can you go back? I think it's go backwards.
Percentage of small.
And another one. Yeah, and oh, I think this one. No.
This one?
Oh, this one. Sorry, the slides 17.
17.
Yeah. 17. Yeah, this one, right? It's a small, yeah.
Yeah.
How like, yeah, like what the percentage mean here? Like 15%.
Oh.
Yeah.
Oh, okay. Sorry. So the percentages, the percentages here are the percentage of the river discharge that exits each channel mouth.
Got it. Okay, I see.
So here we've got about 10, here we've got about 5, here we've got about 15.
Got it. Yeah, that totally makes sense to me now. Yeah, because this is a slide where I jump in your talk and I find, oh, okay, there's so many good data here, and it's great. Okay, thank you. Yeah,
Sure.
It's a great talk. I really like it. Yeah, I enjoyed it
Thanks.
very much. Thank you very much. Yeah.
Yeah, thank you very much, Hongo. In the meantime, we're waiting for more questions. I just wanted to ask, like, what is the influence of the water level fluctuations in those specific deltas that you have? Because, I don't know if they are comparable in terms of like discharge, because the rise of water level could perhaps create less island, create less connection. Oh, sorry, the rise of water level could create like an increase of connection between lakes and the channels. So how do you, take that into account in your analysis?
Yeah, it's a really great question. In this analysis, we have not taken it into account. We have specifically ignored it. So we are only looking at the like low water time at the end of summer, specifically to avoid that problem where we've got these systems can be like totally inundated in May and June when the spring snowmelt flood comes. And the hydrologies of the rivers are all really different, right? So some of those systems are super flashy, other systems have a really long receding limb. And so absolutely, that's going to influence things like the connectivity that we talked about. So we're only looking for this analysis at sort of like first order, what do the morphologies look like at low water times? We can look at the temporal dynamics to try to get a sense of what you're talking about, of how the stage fluctuates, of how the connectivity fluctuates. We looked at that a little bit on the Colville to try to get a sense of the spatial flooding patterns and things like that. But it's difficult to get enough imagery to kind of map that out over time if you're looking for spectral imagery in the Arctic where you've just got like clouds all the time. So that can be difficult. The other thing I will say, though, is I don't know if she's on this call or not, and there's no pressure if she's not, but Claire Hines, the master's student who's been working with me, who did some really neat modeling work in these systems to try to understand the sediment fluxes through the delta networks, and specifically looked at the hydrographs to try to estimate that leakiness based on basically the pattern of the hydrograph and the length of the deltas. And so she has some better estimates than I have even of how much leaking we might have through these systems and what that might mean for like connection and storage in the system. So we do try to account for it in some more recent modeling we're doing. But in this study, we really just try to avoid it and just look at the low water times so that we don't have to worry about the noisiness of the flashy spring.
Nice, thank you. So then those low water discharge were obtained by visually, like you observe the imagery and then, or do you have like gauges near those deltas that ensure you that they'll have low discharge?
Yes, so there's gauges in all of these rivers that give us that information, and so we just based on, you know, there's a lot of interannual variability in Arctic systems, but it is also pretty reliable that it's low water in August because we have a snow melt flood in kind of May, June, and then it does go down. And so the lowest water time you're going to have without ice is going to be somewhere in that August, September timeframe. And so that's the imagery that we tried to pull.
Thank you. Thank you for the answer. Yeah.
Sure.
So I do have a question, unless there's something in the chat, Shashank, is there anything there?
I don't think so, Roberto. Please go ahead.
So you were talking about, you know, how the systems are dynamic and we do all these statistics, you know, in terms of geomorphology on static or, you know, averaged images. And, you know, I have a question in terms of the age of some of these deltas. So you go and compute, you know, I'm just thinking, you know, if you have a very old delta and some of those lakes are potentially have been filling up, your statistics looking at lake area are gonna be different than a younger delta. So that's, you know, any comments on that regard. And the second one is, if, you know, some of your estimates, you say that the Lena has that island, but it still had a bunch of lakes. But that's kind of like apparently like a dead area for the delta. So
yeah. So okay. I'm unpacking that as I'm scrolling through my slides. So yes, that island has a bunch of lakes. I should revise this figure. The actual numbers exclude those islands where they're not.
Okay.
So the terraces are not included in the estimates of like total coverage. So that part is easy to say, like, let's ignore that because it's also like 10 meters above sea level. It's not flooding. So, okay, your other question about distributing, you know, sediments and whether that's causing differences to the lake populations as they fill up, and some deltas might be older than others, or parts of deltas might be, you know, older than others. Yeah, fair point. I will say the lakes can fill up with sediment. They also can grow and expand over time as the permafrost has been thawing. And so I'm not going to pretend on the fly to have a good sense of what that combination of factors will mean quantitatively for what the lake populations look like. I think there's probably an opportunity out there to make and use a really neat thermal model of thermokarst lake development and think about how the rate of input of sediment might affect heat transfer through these systems and therefore the expansion of lakes over time. I'm not sure anyone has really looked at that. I also don't know, thinking back to Hongwo's point about, Landsat resolution, I don't know that we are depositing enough sediments in these lakes in modern times to be affecting them in a way that I would see looking at kind of Landsat imagery, just because of our, our ability to kind of detect land water boundaries is probably uncertain to 1 to 2 pixels. And I'm not sure that we're gonna see a signature of that. I'm happy to be proven wrong. But certainly if you were, if you were looking for like change in the lakes over time, which we haven't really done, then maybe you'd have to consider what sediment input to the lakes is doing. But I think it's more likely that you're just going to see a signature of like lake shore slumping and growth as it's been warming over the last 50 years.
Okay. All right. Yeah. Thanks. I was just curious, about, those kinds of things you're filling up, but you make also a good point. The whole thing might be subsiding. There's also a rebound. We talked about that a few weeks ago. So how do all those things kind of, get played together?
Right. Exactly. It's one of those things that, I should say, there's few science questions that keep me up at night, but there's thinking about the future of Arctic systems with all of these complicated interacting processes is one of the things that terrifies me, right? Because in these systems, like we can model how permafrost develops in the deltas and how that might affect the channel network. But then what about when the permafrost thaws and the ice goes away and you've got subsidence and you've got changes in boundary conditions? There's a lot that we don't understand even about the fundamentals of these landscapes that make that kind of like predictive stuff really challenging. But the lakes are, one part of that story and how the landscapes are going to change. And I don't have a really great answer.
All right. We'll continue to talk then over the next few years.
Let's do it.
I will again ask people who have joined us if they have more questions. In the meantime, I'm going to take that opportunity and I'm going to ask a question about. So I haven't worked on these landscape, and I'm very curious about the influence of actual geographic location on the ice melting. You talked about larger channels melting ice faster than the smaller channels.
Mhm.
I was curious what's the role of geographic location, actually latitude, longitude? Is there a factor there or no?
Likely yes. So,
Okay.
so certainly the easiest comparison, at least I could make, is between like the Colville Delta and the Yukon Delta. So the Yukon Delta, I've like included it with these 6, but it's technically subarctic. So there's a clear geographic difference between the Colville being up on the North Slope and the Yukon being kind of southwestern Alaska. So in the Yukon Delta, we definitely do see that the ice at the coast melts quite a bit earlier than the ice along the coast of the Colville. So there's definitely a difference in the timing of the ice melt and the timing of the river floods that we can see and that we can quantify. So there's definitely a geographic control on the timing of the overall melt, for sure.
And building on Roberto's point, I'm curious, is there a relation between the age of the delta and the number of lakes that we see? Do you think there is going to be a role?
Yeah, that's a really great question. I think that, okay, I have multiple answers. So I think that a large control on the lake coverage is likely the ground ice content. So you need the ground ice to be lost, to lose that volume, to subside, to grow the lakes. So ground ice likely has a large control on lake cover. second answer is that Lawrence Boulis did some cool work on the lakes on Arctic deltas and showed at least that there's some climatic controls on the lake coverage between a lot of these different systems. And so if we think of that, there's, climatic controls, maybe warmer systems have different lake populations than colder systems, then at least over time, as it's warming, you could think of that as being a control on lake cover. Other answer is that I would love for someone to try to model that, to try to figure out if, as the deltas grow, how the lakes are developing at the same time once the permafrost starts thawing, and if you could deduce something about delta ages based on their lake populations. That would be really valuable.
Thank you for that answer. Yeah, I'm curious about the last part.
Yeah.
There's no, sorry, there's a question there in the chat. I'll let them take it.
Yeah, so Toby Minyar is asking that if any luck using SWOT data to evaluate ice, snow, open water elevations, and potential distribution across the channel network?
Great question, Toby. Haven't checked yet. I've at least been, I took a look at the recent SWOT release for the Noatak River that I emailed you about with this, the Noatak River being in Alaska. And I'm at least seeing that, we're not getting any good information yet because it's winter. And so we haven't gotten reliable discharge information from SWOT at least. Whether we could get information about just water surface elevations in these systems, admittedly, I have not checked. But it is possible that, just from the little bit of SWOT data that we have before it all froze up, we might be able to get some information here. The slopes are really low. These systems are super flat. So for discharge, my understanding is that's going to be problematic, but perhaps for just water surface elevations, maybe we could get enough information to tell us, where it's flooding and how much. It's a good idea. It's something we could definitely look into.
So, well, I think it's almost the end of the talk. So if there are no more questions, so thank you very much, Dr. Piliouras, for sharing your research with us. And yeah, we appreciate your insights and we look forward to further findings. So yes, please be in touch with us and with everyone here attending also your talk. So yeah.
Great, thanks. Yeah, it was fun.
Thanks everyone for joining, and hopefully we'll see you again for the next talk in next month.